Greetings. This is the final clip in our playlist. We're talking about optimization here. So I want to show you, just talk briefly about the challenges that we face in this simulation. This is our list of parameters, clearly pretty lengthy, and there's conceivably some sort of innovation that we could achieve or make with each of them, which would lead to a lot of marginal changes, as we've seen in some of the clips in the playlist already. But if you start entertaining multiple changes, the combinatorial blowup is incredible. So while you have the option of just coming up with process innovations based on maybe career knowledge, something you've read in a white paper or a journal paper someplace, fine. But there are other ways of doing this, and we're going to explore that in this playlist, because there is an optimization strategy here that will look at all these possible combinations given certain bounds and try and estimate the best one. Now, with regard to the replication, I want to just make a point here because it's key in this optimization. So we've observed how we change these parameters when you click on simulation main. But there's also, so you can see my model time is specified here, 6:30 minutes. And importantly, the one thing I'm really trying to drive at here is this random seed. So, think about showing up at this hospital in real life and observing it for a day. You certainly would learn some things about it, but you wouldn't have a representative picture of what life is like in this Hipkins surgical workflow unless you came back multiple times, because the people that show up, between 4 and 7 people are getting served every day, and these BMIs could be all over the place. So you may get a day with all heavy BMIs, maybe all light BMIs, and that just wouldn't be a comprehensive look at what's going on here. So you do need to show up on multiple days. And the way we mimic that sort of repetitive observational approach is to change the random seed and rerun it. So we do replications, and that is an absolutely key move. So what we want to do is set this to have random seed. So every run of the model is unique. What it's actually doing there is it's just restarting, or starting creating a new starting point for the number generators, the random number generators, so that the sequence of, for example, inter-arrival times or surgical times, whatever, are novel relative to anything that has been experienced before. And that's why you've seen me replicate 3 or 4 or 5 times and observe the variation in that. That's essentially critical for a fair estimation of the performance. If you just run one time, just not representative. Now, let's dive in. So again, you have the option of doing this subject to whatever guidance is provided by the case owner, doing it manually, and you could plug away and presumably take some time, but it is an option. Let's look at the optimization tool here. So this is something that you may or may not have encountered before, but the basic idea of an optimization approach to a problem like this is to excuse me, consider a whole bunch of combinations. And these combinations are going to be constrained by, guess what, constraints. So for example, one constraint may be that you don't allow more than 4 ORs. And so if I look at the ORs in my model here, where are they here? I've got, I could dedicate, in the base case, you've got 2 dedicated ORs in each of the tracks and nothing in the pool. But there's nothing stopping you from any combination of assignments. Probably you can have 3 in 1, but you could have, as long as you've got at least 2 in dedicated to be in the pool, you should be fine, along with the constraint that you need at least 2 in A and the pool combined. So there's ways of limiting where these variables can go, these parameters can go, so that ultimately, the combinations that are being explored in terms of their performance outcomes are meaningful in the real setting. So we've got those constraints. But then what? All right, so just as you would in a manual exploration of the possible innovations, there's going to be an objective function. You're measuring this somehow. Now, yeah, when you're doing this manually, you're thinking about how many surgeries you're getting, maybe thinking about the costs and how much money you're going to be making. But then there's also those flow times for A and B as KPIs. So in this optimization setting, we're going to capture both of those KPIs somehow in a so-called objective function. So in a nutshell, then, optimization as construed here has a single objective function, which we're expressing here, and I'll detail that in shortly, subject to various constraints. And then we're also allowing certain latitude in these parameters. So that's the net. So let's explore these things one step at a time. So the first thing is, so just a footnote here. This is showcasing the optimization. The way it's set up is probably going to have to be revised, and that will be subject to whatever tweaks the case owner decides. But here I'm optimizing the costs. So I'm clicking on the minimization option here. I can either maximize or minimize, but what I'm looking to do is minimize the sum of all the salary costs and a cost associated with the flow times, because I want them to come down. So I'm going to say that each flow minute has a cost of $10,000. Now, okay, so it looks like apple and oranges going in here. I've got salary dollars, and then I've got some sort of assigned cost of flow times. Fair enough. You may not like it, but at least I've got the profit or the cost of the triple bottom line in my objective function, along with some well-being measure that is of interest to the people in this environment, namely the patients. Okay, so let's have a look at the detail on that. I'm saying, I'm just looking here, I'm looking at the folks dedicated, who are dedicated assignments, surgeons dedicated to tracks A and B. They're each getting paid $375,000 a year. Now, I'm taking out the thousands. I just use 375 to keep it simple. And the dedicated anesthesiologists to track A and B are getting paid $393,000. Where did I get these numbers? I looked them up somewhere on the internet. I don't have a reference for you, and you certainly can revise those. As said, well, this is just a showcasing of the optimization tool. Anybody assigned to the CRNA pool is only getting paid $212. Anybody in the physician's assistant pool is getting paid $127. And I'm going to go and make this a 10. So any flow time in either track, I'm adding those flow times in tracks A and B together, multiplying that by 10,000, or just 10 here because we're excluding the thousands, and that's the cost of the flow times. So to minimize that is my objective. Now, let's go and see how much latitude I'm allowing. What am I going to use as my decision variables? What can this optimization tool go ahead and change in my parameters? I'm allowing it basically to decide whether, how many anesthesiologists, how many surgeons, and how many ORs, well, not how many ORs, there's going to be 4 ORs, but at most 4 ORs. But, in terms of ORs and anesthesiologists and surgeons, I'm allowing it to decide essentially how many to put in place and where and how to organize this. Should they be dedicated to track A or B, or put in the pool? That's the question I'm framing for this optimization tool. All right, so you can see some of these things are fixed, and so they are not going to be decision variables or not going to be manipulable in my in this exploration that the solver is going to undertake. But I am allowing it to go ahead and figure out, how many dedicated anesthesiologists I want in track A, and it's going to vary between 0 and 2. It's going to step up one at a time. So in other words, consider 0 or 1 or 2. Same for B, 0, 1 or 2. And then for surgeons, 1 or 2. Okay, minimum of 1. Same for B. And then for the ORs, you can have 0 or 1 or 2 dedicated to track A, and 0, 1 or 2 dedicated to track B. Also, for the pooled ORs, 0, 1, 2, 3, or 4. And then in the CRNA pool, 0, 1, or 2. These would be additional anesthesiology pros. And then for the PAs, 0 or 1. So that's the range. Now you can go ahead and change these. It's for you to debate. And I'm not saying that these ranges are, meaningful, but this is how we're setting this up. Now, I also have constraints, and I want to lay out what they look like. So I need to have, I'm asking for at least 2 ORs between those dedicated to track A and those in the pool. So that's what I've captured here. The number of ORs in track A and plus the number of ORs in the pool must be 2 or greater. Also got that same constraint just further down here for B. So the number dedicated to B and the number in the pool must be larger than greater than equal to 2. Also, I need to have an anesthesiologist either dedicated or in the pool for track A. So that's this one. And the same thing for B, at least 1 in the pool, and the number in the pool and dedicated must be larger than 1. And then for the surgeons, I'm insisting that we have at least 1. Now, I only am allowing this to vary from 1 to 2. So in fact, these are redundant, but I decided to put them in any case. So again, what am I doing? I'm exploring all the possible combinations of changes as articulated here. Now, I'm not changing everything, but I am basically exploring utilization matters and pooling lenses, giving it a range of possibilities to look at. And it's going to explore all possible combinations, either marginally or interaction type settings, and then price it out using this objective function. And the tool that we're going to use the solver that we're going to be using is the so-called genetic algorithm. You'll see that there are, in fact, 2 solvers here, an OptQuest and a genetic. OptQuest is a third-party commercial solver that is not going to fly here because we have too many decision variables for in the OptQuest only is available for the paid licenses, unless you have a limited number of decision variables, which we exceed. So the only solver we have available is this genetic solver. It's a type of meta-heuristic. So in heuristic optimization, you're looking for strong, robust, meaningful, feasible solutions. You've sort of given up on this idea that you're going to have an optimal solution, but you definitely want something that's pretty good. So there are some weaknesses in these meta heuristics in that they're not finding the optimal solution, and hopefully a close to optimal solution. But just as a footnote, there is no guarantee here. So, and if you run it multiple times, you may get different answers because it could get jammed in local optima. So the genetic algorithm is a class of solver. Other alternatives in this class of solvers would be, if you've explored this before, you may have heard terms like taboo search, simulated annealing, evolutionary search. What else? Maybe end colony optimization, things like this. You may also get special tailored heuristics, which are not available sort of as a general solution approach, but could be developed for a case like this. But it's basically exploring all of these combinations and trying to make sense of it and come up with a proposal for a final solution. All right, so once you've got this thing set up, you have to create a default UI. It's sort of like compiling this optimization problem, so to speak. Just note, there are some other limitations that come from the personal learning edition. And, they are things like 500 iterations. So I'm going to go ahead and create this. And it shows this UI, but I need to run this. And what it's going to be basically doing is in the current thing, you can see the ones it's going to explore. Anything in blue here are parameters that it can vary, and the ones in black it can't. You've got the pooling items here, and you've got the dedicated anesthesiologists, surgeons, and ORs here. And it's going to remember the best one here, sort of graph the progress on the optimization, on the objective function as it goes. So we'll run this. Okay, here it is. And Actually, I need to make it a little smaller so I can see the run arrow here. And the interesting thing about this is it, sort of gives you a real-time update. You can see it's exploring different options here. And this is the best one that it's seen so far. And you can see how it progressively improved here. And I believe it's done. Only had to look at 12 options. And that's because of, the different combinations that were available to it. It turns out we're actually only 12 here now. Whether this is all you want to consider in the development of a solution is for you to evaluate. But of the options that were available, it's suggesting this one as the winner. So it wants to assign an anesthesiologist dedicated to tracks A and B. Of course, there has to be a surgeon dedicated to track B. It's leaving one of the ORs dedicated for track B, and the other 3 would be in the pool. It's also hiring 2 CRNAs and no physician's assistants. And so that's, it reaches this final minimum cost that it's finding of, $5.157 million, composed of course, the salaries and then $10,000 for the flow times. So if you wanted to assess what the flow times and the surgery counts are for this particular setup, you could go back into the simulation and implement this setup. So it's a base case with the exception of 3 of the ORs being pivoted to the pool, and you're adding 2 CRNAs, and you could just price that out by running the simulations. So I think this is a great place to find either very strong starting solutions or final solutions perhaps for this problem, understanding that there's limitations in what I showed you with regard to these parameters that are varying, and then you're going to have to dig in deep here. It's minimizing cost, and just a thought, if all we were about was to minimize flow time and cost, then why not just shutter the hospital? There would be no flow times, 0 flow times, and 0 salaries to pay. So there has to be something more to this problem than the objective function that I have. So I hope this is a reasonable showcase of the optimization option. Of course, you can do it manually, but this allows you to explore a bunch of combinations and their effect, and maybe find strong starting solutions for the rest of your deliberations. Enjoy.